Hi YouTube, this is Mike, and the purpose of this video will be to show you how to analyze video poker, meaning a whole game, not just one hand. And I have a feeling this is going to take a while, so I'll probably break it down into parts. We'll see how it goes. But you can see that I'm starting here with just a Hello World program, and let's take it from here. So the way I do this is to create an array of 2,598,960 possible ways to choose 5 cards out of 52 for the starting hand. And I'm going to score all of them and put all these scores in an array, so I only have to score each hand once. And this will become more clear as we go. But let's start by doing that. And let's do that in a separate function. What should we call it? How about setup? And we're going to cycle through the 5 ways to choose 5 cards out of 52. And we'll do that with 5 variables. We'll call them C1 to C5 for 5 different cards. Oops. And we're going to do 5 nested for loops. So the first one will be for the first card. So that can be anywhere from card number 0 in the deck up to, let's see, the 47th card. So the next card can start, we'll call that C2, will start with being 1 more than C1 up to the 48th card. And likewise for C3 will start out as 1 more than C2. And so on. So this will lead us through all possible cards. And because we start at 0, the last possible card will be card number 51. Okay. So here we've got 5 positions in a deck, but let's create the deck itself. And I'm going to create a structure called a card. And a card will have both a rank, I'll just call that R, and a suit, we'll call that S. And I'm going to create a global variable called deck of 52 cards. And I'm making it global because I have a feeling I'm going to be calling it other places. Now I could pass it around, but why? So let's set up that deck. We'll do that in setup. So let's create yet another variable. We'll call that I. So I is going to go from 0 to 51. So position number I in the deck, I'm going to say the rank is equal to I divided by 4. And if that doesn't round, I'm going to round down. That's what this does right here. And the suit will simply be the modulo of I divided by 4. In other words, the remainder after dividing by 4. So notice how if I goes from 1 to 51, the rank will go 0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, up to 12. So it's already going to be sorted from low to high. So as long as I load in cards from this deck, starting from the bottom and going to the top, they will be in order. I don't need to sort them. Okay? So, moving right along here. So once we know what C1 is, let's create an array for, we'll just call it deal, for the player's card on the deal. So we will say the first card in deal is equal to card number C1 in the whole deck. And we will do that for all 5 cards that we're looping through. So deal 2, deal 3, deal 4, C2, C3, C4, and C5. So now at this point we have an array of cards called deal that has 5 cards in it. So now let's score it. And let's create a function to do that. Next, let's work on a function to score a hand. And let's just call that score. And it will return an integer value to represent the score of the hand. And let's pass it that array, that 5-card array called deal. And I forgot to put the brackets here. Okay, first let's check if the hand is a straight or a flush. So if the suit of card number 0 is equal to the suit of card number 1 and the suit of card 0 equals the suit of card 2, and it equals card 3, and it equals card 4, that will mean that all the suits are the same and we have a flush. Otherwise, we don't. So next let's test for a straight, and I'm going to copy and paste this line and modify it. So first let's make sure that all the ranks are different. And we don't need to test for that for a flush, because if all the suits are different, then all the ranks must be different. Excuse me, if all the suits are the same, then the ranks must be different, because there's only one deck. So here I'm making sure that the ranks are different. So here I'm saying the rank of card 0 is different than the rank of card 1. And I'm going to say the rank of card 1 is different from the rank of card 2. And the rank of card 2, remember that all the cards are in sequential order. And the rank of card 3 is different from the rank of card 4. Okay, that looks good. So if that condition is met, let's make another condition. Now let's do that separately. Okay, so at this point, we know all the ranks are different. So one way we can test for a straight is that if the rank of card 0 plus 4 is equal to the rank of the last card, card number 4. For example, 6, 7, 8, 9, 10 straight. Notice that 10 minus 6 is 4. Another way we can have a straight is that we can have the wheel, ace 2, 3, 4, 5. Excuse me, yeah, ace 2, 3, 4, 5. So let's test that the largest card, card number 4, is a 12, which represents an ace, and we'll say card 3 is equal to a 0, 1, 2, 3 is a 3, which represents a 5. And if that's true, then the other cards must be a 2, 1, and a 0. Because if we're at this point, then we know that they're all different. So remember, this is the wheel. And otherwise, we do not have a straight. And here we're saying straight equals 0 because we found at least a pair in those 5 cards somewhere, meaning a straight's impossible. So here are our tests for a straight and a flush. So if both of these are true, then we have at least a straight flush. So first let's check for a royal flush. How can we do that? Well, with a royal flush goes 10, Jack, Queen, King, Ace, and the rank, our rank of a 10 is an 8. So we're going to say if the rank of card number 0 is an 8, then we have a royal flush. And I hope this isn't confusing. Programmers like to start counting things at 0. So that's basically why I'm subtracting 2 from the rank of the card itself to get what I call it in this program. All right, so let's return a value of 9 for a royal flush. So if we don't have a royal flush, then we must have a straight flush. And let's return a value of 8 for that. So what if we have a flush but not a straight? Then let's return, how about a value of 5 for a flush? And if straight is 1, let's return a value of 4. So otherwise, if none of these conditions are true, then we do not have a straight or a flush. So let's test for a 4 of a kind. So if the rank of card 0 is equal to the rank of card 3, we have a 4 of a kind, with the card number 4 being a singleton. Another way to have a 4 of a kind is that the rank of card 1 is equal to the rank of card 4. And, whoops, that should be an R. So if either of these conditions, whoops, let's put an or here, not an and. If either of these conditions are true, then we have a 4 of a kind. And we'll return a value of 7 for that. So next, let's test for a full house. And let's just modify this code. So one way to have a full house is that the rank of card 0 equals the rank of card 2, and the rank of card 3 is equal to the rank of card 4. So if both those conditions are met, we have a full house, and let's return a value of 6. And there's another way to get a full house. That's where the rank of card 0 equals the rank of card 1, and the rank of card 2 is equal to the rank of card 4. So again, there's another way to get a full house. If that's not true, we already tested for a flush and a straight, so let's go right to a 3 of a kind. So let's copy and paste our 4 of a kind code, and we're going to test that the rank of card 0 equals the rank of card 2, or the rank of card 1 equals the rank of card 3. And there's one more way. That's where the rank of card 2 is equal to the rank of card 4. So if any of those are true, let's return a value of 3 for a 3 of a kind. So next let's test for a 2 pair, and let's modify our code for a full house. So if the rank of card 0 equals the rank of card 1, and the rank of card 2 equals the rank of card 3, then we have a 2 pair. But there's other ways to get a 2 pair. In this first way, card 4 is the singleton. Another way is that the rank of cards 0 and 1 are equal, and the ranks of cards 3 and 4 are equal. And yet another way is that the ranks of cards 1 and 2 are equal, and 3 and 4 are equal. So card number 0, 2, or 4 can be the singleton. If none of those are true, then let's test for jacks or better. So first let's test that card 0 is equal to in rank to card 1, and that card 0 in rank is greater or equal to a 9. So remember the 9 represents a jack. And if that's true, let's send back a 1 for jacks or better. Another way is that card 1, the rank of card 1 matches the rank of card 2, the rank of card 2 matches the rank of card 3, and the rank of card 3 matches the rank of card 4. And let's make sure that we're testing that rank in the pair is a jack or better. So there we go. There's our 4 ways to get a pair of jacks or better. So if we're at this point, we haven't found any ping hand, so we're going to return a value of 0. So moving right along here, let's declare this function at the beginning. And let's go back to our setup function. So let's call score, and that's going to return a number between 0 and 9 depending upon the value of that hand. And what are we going to do with it? Let's declare an array of our scores. We'll call it score array. And I happen to have memorized that there are 2,598,960 ways of choosing 5 cards out of 52. And let's create another variable. We'll call it count. And let's initialize count to 0. So I'm going to say that the value in our array associated with the variable count is equal to what comes back when we call score. And then after that, we're going to increment count. Okay, so let's print out the value of count once we're done, just to make sure that we did it right. And also, just as a test, let's count off how often we get each hand as we go. So let's create an array for that. We'll call that score deal array. So the scores can range from 0 to 9, but let's just make it 52 long, because there's no shortage of computer memory. And we will initialize those values as we're setting up the deck. Oops. And so that we don't have to score everything twice, let's create yet another variable. Let's call it SC for score. So this line right here is going to increment the count of whatever the score is for that hand by 1 whenever it happens. So once we're done, let's see how often we got each hand on the deal. Forgot another colon here. Okay, let's compile this. And it compiled. So let's run it. And it's not doing anything because it never actually called this function. So let's actually call it. And let's declare it up here. And now let's compile this again and run it. And that number of straight flushes doesn't look right. So let me see what I did wrong. All right, I found my mistake. At least one mistake. Right here, I am checking, when I'm checking for a straight, I should have checked that the rank of card 2 does not equal the rank of card 3. I accidentally had an S here, so it was comparing a suit against a rank, and it just goes to show you how screwing up one character can ruin a whole program. So let's recompile and try it again. And here are our results, and there's still too many straight flushes, so let me see what's going wrong. All right, I found another error. When I'm checking for a wheel, there should be 2 equal signs here because I'm doing a comparison. What I did here was I made the rank of card number 3 a 3. I just want to see if it's a 3. It's a very frequent beginner mistake in programming. So let's recompile and run it. And here are our results. And I have dealt with poker-based games enough to know that these numbers are right. So we are ready to move on. We are ready to move on to the next step in this program, which is going to be to cycle through all 2.6 million ways the player can get 5 cards on the deal. And you may say, didn't we already do that? Yes, we did, and that was to score each hand. But now we're basically going to do it again, but it's going to be to give the dealer, the player an actual hand on the deal, which he will be put to the test to play. So we needed to have scored all these hands before we get to this next step. However, the code is going to be much the same as this code for the setup function. So I'm just going to copy and paste it, and let's give it a new name. Let's just call it deal, because we're analyzing the hand on the deal. And let's see, we don't need this. We don't need count. We don't even need score. We don't need to create our deck. We really just need to pick 5 locations in the deck between 0 and 51 for the player's hand. And for each one, we'll go to another function that we'll just simply call draw to determine how the player plays that hand. And let's make another function for that. And we'll change the name of the function to draw. And we're going to pass to this draw function C2 to C4, which are 5 numbers between 0 and 51 to indicate what cards the player got on the deal. But let's give them different names in the draw function. No, let's keep them the same. All right. So now let's change the names of our loops in this function. Instead of C1 to C5, let's call them D1 to D5. D meaning for draw, which I know is confusing because D also is the first letter in deal. But we're going to be using these variables a lot, so I want to keep the names short. So this is just the redundant part of changing the names. And make sure you do this carefully. It's a frequently made mistake, at least by me, to not completely correct myself when I do a copy and paste. Okay. All right. Okay. Let me pause and explain something. No matter what cards the player gets on the deal, he can get any hand on the draw. And he can achieve that because there will be 5 types of cards. There will be the 5 cards the player initially got on the deal and 47 other cards. So between picking cards from both groups, you can achieve any hand. So what I'm going to do is cycle through all 2.6 million ways the player can get a hand on the draw, and I'm going to check which of those cards the player already got on the deal. And I will explain more about why I'm doing this as we go. But I'm going to assign a variable. I'm going to make a new variable called index. An index will range from 0 to 32, 0 to 31, according to the 32 ways the player can play the hand. And I'm going to store in this in an array I haven't declared yet the expected, shall we say, the possible outcomes of all 32 ways to play the hand. But now, for now, let's write some code to see which cards from the deal match cards the player kept on the draw. So here we're going to check that if the first card the player got is equal to the first card, or the second card is equal to the first card on the deal, or the third card on the draw, or the fourth card, or the fifth card. So this is asking did any card the player, shall we say, got on the draw equal to the first card the player got on the deal? And if it is, we're going to increment this value called index by 16. And now let's do the same thing, but checking for the second card, C2, on the deal. And if we find a match there, then I'm going to increment index by 8. And now let's check for the third card on the deal. And if we find a match there, let's increment index by 4. And now let's look for C4. And if we find a match, let's increment index by 2. And finally C5. And if we find a match here, let's increment index by 1. So after this block of code here, we will have a value of index. Now let's initialize this to 0 here, because we will be getting to this step many times. We will have a value of index from 0 to 31. Again, and each value of index will be associated with a way to play the hand. And pause the video right now if you didn't understand that, because this logic is key to the whole program. All right, so let's pause for now. Okay, next, let's keep a count of all 2.6 million ways to play the hand. And we don't need to declare any cards. You know, after this function here is set up, we never need to worry about cards again. It's just all about looping and positions in the deck. So inside this last loop here, we're going to increment count. So count is going to have a value ranging from 0 all the way up to 2,598,959. Okay, so each value, let's create another variable, SC for score. So let's get the score. And what did we call our score array? I think we just called it score array with an underscore. Okay, so now we need to put this score in another array according to how the player played the hand. So let's make a name for that array. Let's just call it the draw score array. So that's going to have, there's going to be 32 possible index numbers and 10 different outcomes of the hand. So let's initialize that array. Okay. So in here, once we know the score and the index, let's increment the appropriate place in the array for the score of that hand. Whoops. So the first value in this two-dimensional array is the index, and the second is the score. And we're going to increment it by 1 according to whatever the index is and the score is. So next, let's figure out the total amount the player wins for any given way to play the hand. And to do that, now would be a good time to decide how much is any given hand going to win. So let's create an array for that. We'll just call it the win array. And let's go with good old 9-6, jacks or better, the gold standard for video poker. And these numbers I'm putting in are what each of the possible outcomes pay. And if you're not familiar with video poker, trust me, this used to be the gold standard pay table. But it's very hard to find anymore. And with this pay table with optimal strategy, the expected return is 99.54%, which I hope to show you later. All right, where were we? So back here at draw, let's create yet another array for the total win. Let's just call it the draw win array. And that's going to have 32 possible values for the 32 ways to play the hand. And let's initialize that. Okay, so let's go to the bottom after we've cycled through all the ways to play the hand. Let's increment to this draw win array. Okay, we have to cycle through all 10 ways the player possible outcomes of the hand. So we're going to multiply how many times the player got any given hand for any given way to play the hand by the win array. Okay? So that will give us 32 different wins. However, we can expect the win to be really high for throwing away everything because there's about 1.6 million ways those replacement cards could come out. And if the player holds everything, there's only one way the draw will happen. It is just whatever the player kept on the deal. So we need to weight all of these 32 possible combinations of the ways to play the hand according to how many combinations there are on the draw, so that so basically This is a little hard to explain, but we need to compare apples to apples. So we're going to multiply the plays where the player keeps more cards by a bigger number. And this will become more clear as we go. Okay, this next part I'm going to do in Excel, and it will save time in the program itself from doing the same kind of calculations over and over. So I'm creating this index here to represent the 32 ways the player can play the hand. And so there's 5 different cards, and with any given card the player can either keep it or discard it. So I'm going to do some binary arithmetic here to convert the index to 5 different numbers that are either 0 or 1. And I don't want to give a lecture right now on how I'm doing this. But in short, I'm dividing the index by some power of 2, and then dividing that by 2, which will give me a remainder of 0 or 1. So here we go. This is every possible sequence of 5 binary numbers. And a 0 shall represent throwing away the card, and a 1 shall represent keeping it. So let's take the sum of the number of cards the player is keeping. And let's also look at the number of ways, I'm going to call it draw combinations, the number of ways the player can get cards on the draw. So I'm going to use the combin function for that, which I love. So there's always going to be 47 cards left in the deck, and that's going to be the number of ways to choose 5 minus the number of cards the player is keeping from 47. And let's copy and paste that down. Okay, so why did I do that? This is a little hard to explain, but eventually I'm going to have to weight the best play according to the number of draw combinations. For example, if the player throws away everything, there's about 1.6 million ways the player can get cards on the draw, but if he keeps everything, there's only one possible hand that he's going to get on the draw. And so I'm going to need to multiply every possible way the player holds his cards to get at the same product. Again, I know this is a little difficult to explain, but I think that as we go, you'll see what I'm doing. And let's find the least common multiple of all these numbers. And that can't be right. Let's see what happens if we divide this 1,533,939 by any given total. Okay, so we can see some 0.6s in here, meaning that, for example, 178,365 does not divide evenly into 1,533,939. But if we multiply the numerator by 5, then it should work. Okay, so this will give us weighting factors. And we basically need to throw these numbers into an array. So what I'm going to do is I'm going to add commas to these values. and copy and paste this down. And I'm going to take away the comma from the very last entry and then concatenate all these values for all the different index numbers. So this gives us an array of, hold on. Yeah, gives us an array of the number of combinations on the draw, and doing the same thing to column K will give us an array of the weighting factors. Okay, next what I'm going to do is I'm going to copy and paste those array values into my compiler. So let's put them on different lines. Copy and paste. And let's make them global variables so I don't have to keep calling the same numbers over and over. And let's call this array of draw combinations, we'll just call it draw combinations array. And let's call this other sequence of numbers the weight array. No, how about the weighting array? And let's go to the end here to close out these arrays. Okay. I'm just going to copy this down to the draw 5 array just so I can remember what I called them. Okay. So, you may recall we left off is we have this draw win array that shows the total win for all the ways the player can play the hand. And did I declare that as an integer or a float? Let's declare this as a floating as a decimal instead. So now after I have this total win, I'm going to divide it by the number of combinations. And I'm copying and pasting the name of that. There. So that, after this division, we should have some value between 0 and 800 for the average win of all ways to play the hand. It occurs to me that I don't really need to store the expected value of all 32 ways to play the hand. I only need to know the best one. So let's create a new decimal variable called max EV, which will represent the best expected value, the highest expected value for the way to play the hand. And okay, let's just call this EV for now. So the EV will be the expected value of any given way to play the hand. And you can see I'm cycling through 0 to 31. So I'm going to do this calculation for all 32 ways to play the hand. And what we want to know is what is the highest. So as we're going through, let's check that if EV is greater than the maximum expected value we found so far, then the maximum expected value we found so far will be that expected value that we just found. And also we need to do one more thing. Let's create an integer called best play. And that will represent the index of the best way to play the hand. And we'll start that at 0. But if we find an expected value that's better than, or excuse me, higher than the one we've already found, then we will update best play for that index value. So there we go. This is some very important code here. Pause the video if you didn't understand everything that I just said. But by the time we're done with it, we should have the index value in this variable best play for the best way to play the hand. All right, next let's compile this thing to clean up any errors we've made so far. So I got rid of this draw win array. So let's remove that. Okay, let's declare, and I know it's not going to like these. And yes, again, let's I don't think we declared either draw or deal at the beginning, so let's do that. Oh no, here they are. Why doesn't it like this? Okay, up here I called it deal 5. I mean draw 5 when it should be just draw. So let's do another compile. Deal 5 is unidentified. And yeah, so that, to be honest, I think I did this when it wasn't on camera, but I should be calling just deal. Okay, so here's deal, and let's declare it at the beginning. Okay, so it at least compiles. So that's fixing up some mistakes. One thing I forgot to do was to initialize EV for all 32 ways to play the hand. So once we get to the end of this function, we should have our best play and all the possibilities that come from it. So now we need to add them to some kind of an array for the whole game. So let's do that. So let's loop from 0 to 9 again. And let's just, how about, let's just call this array total combinations. And I will have to declare it at the beginning. So recall that we put all of the combinations in this draw score array. And the index is going to be this best play. And here we're just cycling through j from 0 to 9. So let's declare this array here. Let's make it a global variable, and we're going to make it a 64-bit integer because the numbers in it will get pretty big. Oops. And I forgot the T. And let's initialize those values. Let's just make it of size 52 so we can initialize it here. Okay, so next we need to print out the values. So let's do that. Let's go high to low. So let's start with I. I is greater or equal to 0 and I minus minus. And I like the printf function for printing out things to a file. So first we're going to print an integer, then a tab, and then let's print out what each hand pays in case I forget, and another tab, and then the total combinations. And then a carriage return. So we're going to send it I. No, I forgot. Let's send it the name of the hand. So that was hand name array. So that's printing out a string. And then, what did we call the win array? Where was I? Yeah, win array of I, and then total combinations of I. And let's compile that. And it compiled. Let me make a couple captions here. So in this line, when we print out a 64-bit integer, it should be percent capitalized 64 lowercase I. And we don't need to declare this array of cards. And also, let's keep a count of the number of hands as we're going through dealing them out. And let's say that, let's print out an update every 1,000 hands. Let me make a couple corrections. So here, when I'm looking to print out an update every 1,000 hands, what I'm doing is I'm dividing count by 1,000, and then I should check that if it's equal to 0, then it prints out an update of count. Before it wasn't doing anything. And down here in draw, I forgot to apply my weighting factor. And what did I call that again? Weighting array. Okay. And I think this program is now ready to go. However, I have a suspicion that's strongly based in experience that it's going to take hours to run. So I'm going to keep a track of how much time it takes in case it finishes while I'm asleep. So I'm going to include a library called time.h. And here at the beginning, I'm going to set a couple of time variables. I'll call them beginning time and end time. So let's set beginning time equal to the time that we start. And this function here, time, returns the exact second according to the computer's clock that this step is executed. And it started counting time, I don't know, like in 1950, sometime back then. And it's just a count of how many seconds since this starting time. Now let's do a printf statement. So we're going to send it to the end time minus the beginning time. And the compiler may not like that statement because I'm sending it times and then doing an integer calculation on them. But let's see what happens. No, it did not okay, well, I got a warning. So let's convert these to integers and see if the compiler likes that better. Okay, so we're ready to run this thing. It is the next day and the program finally completed. So let's have a look at the output, shall we? So I had everything go to this folder here in this file called jax96. And let's pull this over here. So here is the output of the program. So let's copy and paste that into Excel. So here's the hand, here's what it pays, and here are the combinations. Here's the total. So let's sum all these combinations, and we get a number that is almost 20 trillion. And let's make sure that this is the right total. So here's the number of ways to choose 5 cards out of 52. We'll call that the combinations on the deal. For the draw, we have the number of ways to choose 5 cards out of 47. And you may recall that we had to throw in 5 to get everything, all the combinations to be nice integers. So let's take the product of these 3 numbers. And yay, we get exactly the same thing. So let's find the probability of any given hand by taking the number of combinations and dividing by the total. And now let's get the return from any given hand, which is the win times the probability. So let's copy and paste those all the way down and take the totals. And let's make everything have 6 decimal places. 3, 4, 5, 6. Okay, so here we go. Cell E12 shows a return of 99.5439%, which, take it from me, is the right number. It's on my website. It's on other legitimate books and resources about video poker. So there you go. Okay, let's look at how much time it took. It took 49,371 seconds. So there's 3,600 seconds in an hour. So that means that it took 13.71 seconds. Let's find out the number of minutes. Okay, so it took 13 hours and 43 minutes. So there you go. That was kind of a long time. But there's ways of speeding it up. And let me tell you about that. So this is my website, Wizard of Odds. It's at wizardofodds.com. That's O-D-D-S, not O-Z. And let's click on Video Poker. And then let's click on Advanced Video Poker. And go down here to Video Poker Methodology. So here's where I explain how you can speed up this program significantly. So as you've heard me say many times, there's about 2.6 million different starting hands. However, there's really only 134,459 types of starting hands. For example, there are 4 ways to get 4 kings and 1 queen on the deal. It doesn't make any difference what suit the queen is. They're all equivalent situations. So you don't need to analyze all 4 of those. You can analyze just one and multiply it by a weighting factor of 4. So I go through and I show you all the different ways to arrange the suits. I start with 5 unique ranks, and then I go down to the ways to arrange them with a pair, a 2 pair, a 3 of a kind, full house, and a 4 of a kind. And that will reduce the programming time by the computer time by 95%. However, you can get the time down to just 1 second. And this way is kind of complicated to explain, but it does not involve looping on the draw. It's all, shall we say, mathematical calculations and pre-stored arrays. And I explain it here on my site. I'm not going to go through it right now. So that brings me to the end of this video. So I think it may set a new record for my longest video. So thank you for making it all the way to the end. I plan to post this code on my website, and I will put a link in the video description. So give this video a thumbs up if you learned something from it, or shall we say, thank the effort. And I will see you in another video. Thank you again, and goodbye.